All right. Um, so I did, in fact, write the exam over the weekend. I didn't write it Saturday. I wrote it yesterday. The two questions that I promised would be on the exam are on the exam. It is two parts. The first part is topics in introductory Java, just like the midterm. And the second part is applications, just like the midterm. The exam is open book, closed notes. I honestly don't know if the book will actually help, but you can use it. Actually, it probably should. The first question has to do with, two related topics. Has to do with overriding and overloading. One is used when we're dealing with inheritance and we want a subclass to behave a different way than the superclass, and that's overriding. And overloading is when you have two methods with the same name that take different types and numbers of arguments, so that in different circumstances you can use the same method name and it has a slightly different behavior. The next question has to do with the keyword static. The third question has to do with object-oriented programming. Those three key points: encapsulation, polymorphism, and inheritance. It would be good to know what they mean and how they relate to Java, how they manifest themselves in terms of Java. The fourth question is one of the questions that I promised would be on the exam. What is the difference between an interface and an abstract class? The fifth question has to do with exceptions, and it's more of a philosophical question. It's not how do you use exceptions, how do you write your own exceptions, how do you throw exceptions. It's more how do they work and why. The sixth question is the other question that I promised would be on the exam, and that is, what is recursion? And that will hopefully be answered today. Part 2 has 3 questions, just like the midterm. 30 points, 20 points, and 50 points. I remember when I was originally talking about the final exam, I said there might be 2 of one type and 1 question of another type. I didn't remember what I said when I was actually writing the exam. So I think there did end up being 2 questions of one type and 1 of a different type, but it may or may not have been exactly what I said in class. So question 7 is problem solving, and it's a continuation of question 7 from the midterm. So now that we know a little bit more about some of the things that are necessary to do some of the things I talked about in that question of the midterm, how does that affect how you're going to solve the problem? And I'm a little bit more specific, now that we've talked about more concepts, about how I, as the end user who doesn't know anything about Java, how I want this program to work. And it's and it's not solve the problem, not write pseudocode or anything like that. The last sentence is describe the concepts discussed in this course that you would use. So we've learned several different concepts in introductory Java. Which ones of those concepts would you put to use, and what would be the purpose in using them? So if you would use an array, say that and explain how you would use an array. If you would use some form of loop, explain why. That sort of thing. That question is mainly testing not only can you regurgitate these concepts, but do you know when you would use these concepts as well? Question 8 is draw a class diagram. We didn't go in detail about specifically what lines and what organizations use in drawing a class diagram. So I'm not looking for you to use exact UML. In fact, if you did draw exact UML, I probably wouldn't know the difference. I'm pretty shaky on my UML. I just want to know what classes you would use to solve this particular problem. And major hint, it's a problem you're familiar with. It's a problem that we've dealt with before during the course of the semester. So draw boxes for the classes that you would use. Inside each of those boxes, name the class, demonstrate what type of data it's storing and what type of interaction it has, and then draw lines between the boxes indicating how they interact with each other. Is one class used by another class? Does one class inherit from another class? Those sorts of things. And the final question, which I hope I was specific enough without using too many words that it became vague. The actual question is a nice-sized paragraph. The overall theme is top-down programming or top-down design. I present a problem. Hopefully a problem that you're familiar with, not so much from using the end product of this, what will eventually become a program, but you've seen other people use it. And the idea is break down this large problem into smaller problems and tell what those smaller problems are. Any questions on the content of the exam? Alright, so today we get to talk about recursion. Someone who read the chapter, does anyone want to summarize recursion in a sentence? Basically answer the question that will be on the exam. Anyone? Did anyone read the chapter? It's always a good first question. In the other class, I asked that question, and then someone responded sometimes, so I asked him what the chapter said, and he said, well, I didn't read it this time. Right, so I assume the answer to this question is something like the first sentence of this chapter. No, not really. On 804 there is a definition. Ah, yeah, that's close. I guess it technically defines recursion on page 801 with the sentence, the general topic of recursive methods is called recursion. Very helpful. Okay. I think the paragraph before that on page 801 is a better definition. Whenever an algorithm has one subtask that is a smaller version of the entire algorithm's task, it is said to be recursive. So the basic idea here is rather than simply performing top-down design or top-down whatever, top-down insert something here, where you take one problem and divide it into smaller problems, solve those individual problems, and if those are still too big, you break those down further and further, and get this tree of subproblems. When a problem lends itself to recursion, you take a large problem, break it down into multiple subproblems, usually one or two. Any more than that, and there's probably a more efficient way to do that. But it turns out that each of those subproblems is identical to the larger problem, but just dealing with a smaller amount of data or something like that, which makes it more manageable, more easy to conceptualize, easier to deal with. And the classic example of this is the factorial. Is anyone not familiar with the factorial? Awesome. Oh, before I forget, again, the last homework assignment is due tonight, right? So the last homework assignment is due tonight. To make everything go really smoothly, so that I can grade them and post your grades to Blackboard as soon as possible. Make sure that when you submit your homework assignment, only one zip file with all of the relevant Java files for this assignment. That way I can run my script and it'll zip all your files, run them, and I don't have to move files around. Make sure that you send a zip file. We haven't had any problems with that in a while, but make sure you don't send it as a RAR file. I know these computers like to save things as RAR files. Make sure it's a zip file. And these computers also don't really show extensions. So in the right-hand side, where it says file type in the file listing, make sure it says zip file and not RAR archive or whatever. Make sure you send the .java files, not the .java tilde files. Again, these computers like not showing you the extensions. So if you see an extension next to the file that you're zipping up, it's probably not the right one. The file that you're zipping up should have a little icon with a G on it, because for whatever reason they're associated with the program JGrasp. Again, in the file type column, it'll say Java file, whereas the .java tilde files that I don't want say something like Java tilde file or something like that. Something that indicates that it's not the right file. Yeah, and other than that, make sure you get it in on time. I think that should alleviate any issues. Yes?
This course is out of 1,000 points, and you have 1,100 possible.
Correct. So if you've gotten perfect on everything, you could not turn in this assignment and still get 100. You can't get higher than an A in any course in UCCS. So if you get more points than 930 or more points in this class, and you have an A, I can't give you more than that. It's an A. 930. Right. Yeah. Right. I think that's it. So, programming assignment 7, we have the exam, and that finishes out the semester. I will grade the exams on Wednesday after class and post them hopefully Wednesday night. That means that your grades on all of your grades will appear on Blackboard. I have no idea if there's a sum of all numbers column on Blackboard. I have no idea if it's anywhere near accurate. But you have access to all of your grades. You can compute what your grade is actually going to be. I don't remember if I mentioned this at the beginning of the semester, but the sets of 10 goes A, B, C, D, F, and then within those, with the exception of A, it's 0. If the one digit is 0 through 2, it's a minus, and 7 through 9, it's a plus, and everything else, it's no modifier. So you can figure out your grades, and I'll also post them to the portal or whatever it is after I calculate them all. I step onto a plane at 6 a.m. on Friday, so your grades will be posted well before then. I have no interest in posting grades while I'm sitting in the Denver airport in between flights, let alone in the Seattle airport at the end of my flights. So your grades will be posted Thursday night at the latest. Right, so recursion. So factorial. So right now I'm doing essentially top-down programming. I'm saying I want to print out the factorial of 5. Right now I don't want to deal with how I'm going to compute the factorial, but I know I want to compute the factorial. So I'm going to make it look like I'm calling another method. I'll write that method later. Later being right now. So the definition of factorial is that you can take the factorial of an integer. It doesn't make sense to take the factorial of a fractional number. And the result of doing the factorial computation is an integer. And the way that works is you take the starting integer and multiply it by the number, that number minus 1, that number minus 2, that number minus 3, and so on and so forth in some sequence, and that last digit is 1. So factorial of 5 would be 5 times 4 times 3 times 2 times 1. Also, the factorial of 0 is defined to be 1, just to make things easy, I suppose. The factorial of a negative number does not exist. Forget undefined. It's just bad. Don't do it. So, since we have the factorial of 5 is 5 times 4 times 3 times 2 times 1, it is also 5 times the factorial of 4, because that last bit is 4 factorial. So we can write this for now in a single line, assuming we spell everything correctly. Num times factorial of num minus 1. What's the problem we have here? If I write no other code, what will happen? Yes. And so we've seen this before, kind of, if we write an infinite loop. The big difference between infinite loops and infinite recursion is infinite loops just keep spinning. We can kill them. They don't take up any extra resources. They just make the CPU really ramp up and not do anything. It does nothing really, really, really fast. Infinite recursion, on the other hand, every method call has some overhead. It has local variables, in this case num, and it has some information about the method, where it's being called from, and that sort of thing, which takes up memory. So when we have infinite recursion, we have to store all that stuff somewhere. And then we make another method call and have to store that stuff somewhere. Make another method call and have to store that stuff somewhere. And eventually, little secret, that's stored in a stack called the call stack. Eventually that grows and grows and grows, and eventually we run out of memory. Or with Java, the Java virtual machine, the Java runtime, kills that and says infinite recursion. You can't do that. So if I were to compile and if I were to save that, compile that, what did I, oh geez. I guess I was a little excited about recursion. One of the downsides of Java, in order to write anything, you have to write this big, long method signature just to tell it where the entry point is. Yeah. It's identical. I've seen, I think this book does it one way and the other book does it the other way. It's a convention and people will argue about it until Java is way beyond obsolete. So yeah, it really doesn't matter. Though that does look kind of goofy, now that I look at it. Yeah, let's do that. Okay, compile. And eventually it will, yeah. You can see the stack trace is lengthy, and all it is factorial is calling factorial is calling factorial and stuff like that, and we get a stack overflow error. That means that we've exceeded what Java can store on its call stack, which is bad. So this means that we need some way to stop this. And there are different approaches for choosing what is called the base case, or some people call it stopping condition. I think the official term is base case of recursion. One approach is to choose the last case that makes sense. So in the case of factorial, the lowest valid number to take the factorial of is 1. Which is one valid case. We can say if num equals 1, return 1. And that would solve the problem. As soon as we get down to 1, it would return and go back up, basically go back down the call stack or go back up the tree of method calls and eventually return, oh geez, what is that, 120? The other option, and the option that I prefer, is to pick the first case that doesn't make sense, that is invalid. So in the case of factorial, it would be factorial of 0. I like that because it follows the mathematical definition of, technical term is recurrence relation, but it follows the mathematical definition of something that's recursive exactly. So the definition of factorial has in math, has two clauses basically. One is the general case, where it's n times n minus 1 times n minus 2 dot 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 n dot 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 1, and the other one is factorial of 0 is defined to be 1. So there are two clauses there. I like to reflect that in my recursive algorithms as well. So instead of saying defining in my code the factorial of 1 is 1, I would say the factorial of 0 is 1. So that's basically the first case that does not make sense. And what would happen here is I'd end up with 5 times 4 times 3 times 2 times 1 times my base case where I'm saying this does not make sense, and that would be times 1. So either way, we end up getting 120. And there are actually two ways that we can get infinite recursion, both of which equally bad. The first one we've already seen, failing to provide a base case. We need some way to stop this recursion. And the other part, so we have the base case, that's one part of this recursion. The other part is our approach. Some way of, it's sometimes called the recursive call, when we call the method again. And so it's often called the approach because that's how we're getting closer to the base case, solving a smaller subproblem, essentially. But if our approach doesn't actually do anything to approach that base case, we also have infinite recursion. So if instead of return num times factorial of num minus 1, I did return num times factorial of num, that would also create infinite recursion because I would never actually reach my base case. So in any recursive method, you need those two parts, the base case and the approach, which is not all that different from loops. Though with loops we usually also talk about some initialization phase. With recursion, the initialization is the first call to the method that ultimately is recursive. With a loop we have the initialization, some condition, which is our stopping condition, our base case, and we have an approach. And I think I used exactly the same terms when we were talking about the for loop. Questions on recursion? What's it?
So it makes it recursion that it's calling its own method?
Correct. It is a method that calls itself. Technically, this method does not provide for all cases. Well, it kind of does. It will, but it's not exactly the right cases that we intend. I've mentioned that the factorial of a negative number does not make sense. And right now, if we have a negative number, it's not equal to 0, so we'll continue this recursion, and then we have infinite recursion. That's bad. So even though it's not technically the definition of recursion, of factorial, I usually do that. Since the factorial of a negative number is not, it's not even not defined, it does not exist. I don't think returning 1 is too terrible, though mathematicians would probably disagree. But it's something that will prevent infinite recursion, which is always a good thing. So if you pass a negative number to factorial, it'll just return 1. You passed an invalid value, so an invalid value back. I think that's a not too steep a price to pay to prevent infinite recursion. Another option would be something like throwing an exception, now that we've talked about exceptions. Personal preference, I don't like exceptions, so I try to avoid throwing them at all costs. But I'm also a C programmer, so. Factorial is a fairly contrived example for recursion, and the book provides some less contrived examples for recursion, one of which I kind of like. That's the merge sort example. Merge sort is a sorting algorithm. It is not the most efficient sorting algorithm, but it is also not the least efficient sorting algorithm. But it's a sorting algorithm that can be accomplished using recursion. So, no. So there's my main method. Have I talked about test-driven design in here yet? I'll take that as a no. So test-driven design is a really cool software engineering technique that's, I guess, started taking off about 5 years ago, and seems to be gaining decent traction anyway. The idea behind test-driven design is that you write your tests first, assuming that they will fail, and then write code to satisfy your tests. The idea being that when we solve problems, we usually enter the problem-solving room, playground, with some set of requirements that our solution needs to fulfill. And we can test those requirements. Requirements should be testable. So we should be able to say, if I have a method called do X, and I give it a particular value, I expect a different value to come out. I can define, without knowing how the problem is actually solved, how the details work, I know, given a particular value, there's a specific expected output value. And rather than writing the implementation first and then testing that implementation, you write the test first before you write the implementation. And before you write the implementation, you know that whatever test you're running is going to fail. That's okay. You need to write your test first, then build an implementation that first satisfies the test, and then secondly, does what it's supposed to do. So, and the idea is that for any piece of functionality, you have multiple tests, so it's very difficult to satisfy all those tests without actually implementing the right implementation. So here, obviously this will not compile because I haven't written the merge sort method yet. So let's write that. So the first stage of test-driven development, test-driven development is writing the test, which is, in this case, is my main method. There are other more formalized ways of writing tests, something called unit testing, but that's outside of the scope of this class. For now, we'll use our main method as our test. Step 2 is something called stubbing. And stubbing involves writing just enough of a method to make the compiler happy. So that means satisfying parameters that need to go into the method, return value or return types, and the method name and stuff like that. So basically getting the method signature right and then getting rid of any other compiler errors. So getting the method signature right. This needs to return, well, first of all, this needs to be static. It needs to return an array of ints. It needs to be called merge sort. And it needs to take in an array of ints. And we'll call this, we'll just use the same names. Call it unsorted. Now, if we try to compile that, it will complain that it's not returning anything. So we have the method signature right, but we need to satisfy these compiler errors. So we need to return something, and it needs to be something of type int array. We're getting unsorted in, and it is an int array, so let's return that. Okay. So it compiles. Step 1 complete. This is a method stub. It does just enough to get the program to compile, but really doesn't do any of the functionality. So now we can talk about the details of merge sort. The way merge sort works is that it divides the array, the input array, approximately in half, and performs merge sort on each piece. At the end, after those two pieces of the array have been sorted, it now has two sorted arrays that it kind of zips up, hence merge. It merges these two arrays. So because there are basically two unique components here, we'll write two unique methods. So one we've already started writing, called merge sort, and the other one we'll call simply merge. So we know we'll have two calls to merge sort on pieces of the array. And we'll have a call to merge on the two results of that. So let's talk about the inputs and outputs to each of these steps. Merge sort, right now we're taking a single array. But since we're talking about a piece of the array, we should somehow specify that particular piece. Rather than copying pieces of the array into other arrays and doing other such messy stuff, let's just specify the beginning index and the ending index. So here, this will be 0. We'll start at 0, and this will be something in the middle. Here, this will be the next one, mid plus 1, and the last index. So unsorted dot length minus 1. Right. So we can make kind of an arbitrary decision here whether that second thing we specify is the last index, which is what I have here, of the piece of the array, or whether it should be either the size of that piece or the one index past the last index of the piece. I think it makes sense here to talk about it in terms of the last index of the array, of the piece of the array that we're dealing with, just so we don't get confused. But since we're adding 2 extra arguments here, we should probably add 2 extra parameters here, and we'll call this int begin and int end. Which means, since we're calling the same method from a whole bunch of different places, we need these changes to be reflected everywhere. So here we're sorting from index 0 to unsorted dot length minus 1. Which, let's say we're further down this merging process. If we're somewhere in the middle of the array, that second piece should not end at unsorted dot length minus 1. It should end at the end of the piece we're currently dealing with, which is called end. Right? Questions on that? So this midpoint, if there's an odd number of elements, it really doesn't matter which piece has one extra element. It doesn't make enough of a difference in terms of speed. So we can simply do the average of begin and end. Begin plus end divided by 2. That will get us an integer somewhere in the middle of the array so that we can break this bigger array approximately in half. That's good enough. So now merge sort, the method, will return this an array that is sorted. So we need to hold on to that so that we can merge those two back together. So int array lower half and int array upper half. And then merge by itself doesn't really make sense. We want to merge a lower half and an upper half. So lower half, comma, upper half. And now instead of returning unsorted, which doesn't make any sense, merge, the way we will define it, should take in two arrays and merge them together and return the resulting array. So that's what we ultimately want to return. Questions? So now we've implemented our approach. We do need to specify our base case. Anybody have any ideas as to what the base case should be? Because of what we're doing here, there are actually two base cases, and there are actually two possible sets of two base cases. One possibility is that we check to see if begin and end are, or if end is not greater than begin, is probably the most appropriate way to do that. We know that we have, no, if n is less than begin, we have, the pointers have gone on opposite sides of each other, which actually can't possibly happen because of the way we're calculating mid. So the most appropriate way to handle this is probably to see if the piece of the array that we're dealing with has one element or it has two elements. If it has two elements, sorting that is as simple as making sure they're in the right order, and if they're not in the right order, swapping them. If we only have one element in our piece, an array with one element in it is by definition sorted. So we don't have to do anything. So let's do that. So this case one. End is equal to begin plus 1. This means that there is only one element. No. Hang on. If end is equal to begin, that means they're both pointing to the same element. So the end index of our piece of the array is the same as our start index of the piece of the array, which means that our array has one element in it, which means that it is sorted. So let's see, what's the easiest way to do this?
Can I actually do that? That would be pretty awesome if I could. No, I can't. Ah! Okay. So, let's... We are smarter than the Java compiler, so we can do... I can do what I wanted the Java compiler to do. And that would have been... that. And that works fine. Why the Java compiler can't figure out that that's what I want to do, I don't know. Case 2, end is equal to begin plus 1. And this would be that begin points to one element, end points to the next element. The smaller array that we're dealing with contains those two elements. If end equals begin plus 1, do the same sort of trickery. Int temp equals unsorted then unsorted and return temp. The problem is that we want to make sure that unsorted begin and unsorted end are in the right order. So we can do that relatively easily by adding another if statement in there. If unsorted begin is less than unsorted end, if that holds true, are they in the right order or are they in the wrong order? That means they're in the right order. So we'll say temp equals that. Otherwise, they're in the wrong order. And I'm actually going to change this to less than or equal to, and the reason I'm doing that is something called stability. A sorting algorithm is stable if when two elements are encountered that are equivalent in the unsorted list, they appear in the sorted list in exactly the same order. So if I have two things that have the value 4, they should end up in the same order in both the unsorted array and the sorted array. That doesn't really make all that much of a difference when we're sorting just arrays of numbers. But when those numbers start getting tied to other things, which you'll talk about in data structures, when you talk about maps or dictionaries, or every language has their own way of talking about them, where the value that you're sorting on or the value that you're selecting on or something like that points to some other data object. So if I had one 4 that pointed to a double or something, and another one that pointed to a string, and I expected them to be in the same order when I put them into an array and when I sorted that array, that would require a stable sorting algorithm. So this means that if these two are equivalent, if unsorted begin equals unsorted end, they will go into the array that I'm returning in exactly the same order. So now I've handled my base case. And if I compile, it complains about something. fine. We can play along. This is a game called What Makes the Java Compiler Happy? Can anybody tell me why that was an error? It's okay if you can't. It's one of those nuanced things that it makes sense when you hear the explanation. So I declared an array of an int array of temp outside the if, then gave it a value inside the if, and then tried to return it. And it was complaining about the where I was assigning it to basically an array literal. Any ideas? Well, yes, but there's a more in-depth answer. The reason is that when you declare an array, Java's fine with you declaring an array that doesn't have a size. But when you try to assign an array to it, you have to give it a specific size. In this case, where I was declaring an array literal, what ends up happening is that Java thinks it has no idea what size that is. So what I'm doing here is doing the declaration and the initialization all in one step, so that when the Java compiler figures that out, it can figure out that it needs to create a new array of size 2 and fill it with those 2 elements. With the other arrangement of statements, it, for whatever reason, couldn't figure that out. So with some messy code, that solves the problem. Now, the only thing we have to implement is this merge thing. Because right now it'll, well, oh, yeah. Don't need that anymore. Compile. It says no merge. But everything else compiles. So, merge, and this takes 2 integer arrays. A and B. Any ideas on how to merge 2 arrays that we can assume are sorted? Yes, that's definitely a good starting point. Right, so we end up needing two ints. And 2 ints are actually sufficient. We also have to have something to put the merged array into. So we'll say int that we'll call it destination equals new int. What's going to be the length of this new array? How much space do I need to make in order to store all the contents of A and all the contents of B. Wow, that just gave away the answer. Anyway, close. What attribute of A do we need? And B, actually. Length.
So A dot length plus B dot length.
And that gives us a new array of size big enough to store the contents of A and B and no more. That and no more is important.
So now, I think you could probably actually combine all of this into a big for loop. The part at the beginning would be very large though, so do while. While A pointer is less than A dot length and B pointer is less than B dot length dot.
So what this is going to accomplish is, as soon as we advance one of those pointers beyond the end of the array that it's associated with, that's it, we're done. With this part, anyway. Because we know that if there's anything left in the other array, it's bigger than everything in the array that we've already exhausted. What goes inside this while?
There's a hint. So now we need to choose. So right now, A pointer is 0, B pointer is 0. Each of those pointers are pointing to the first element in the array A and the array B. We want to choose the smaller of those two elements. So this is basically a switch. Not a switch in the Java sense, a switch in the, train yard sense. If there's one case, we go down one track. If we're in the other case, it goes down another track. So this would be if A pointer
Now let's think about this and try to maintain stability. So if two things are equivalent, we want the thing in the A array to appear before the thing in B array. So
if A, that pointer is less than or equal to B, that pointer, B pointer, and we'll do the or equal to because in this step we'll choose the element in the A array. And this should end up being what index into the destination array should we store this particular value in? So put question marks there for now. The value that we're storing is that, and just to jump ahead a little bit, we're incrementing a pointer.
What position in the destination array should we be storing this particular value in? Yes.
Right, but based on, so eventually we won't be dealing with the first element anymore. How are we going to figure out that that index. It is. Would you like to explain why it's A pointer plus B pointer?
Because they're both, the first one, so if you have 0 and 0, it's going to be 0, and then if you increment 1, you got A pointer is going to increment to 1, and then you want to be no, I'm sorry, I don't know how to explain it.
It's
But you always want it to be, and then if you increment A pointer before you increment B pointer, so B pointer is still 1, you still want it in the second thing, because A pointer will be a 2.
right. So the A pointer and B pointer are also counting the number of elements we've already merged, essentially, from each array. So the total number of elements that we've put in the sorted array is just the sum of those two. And the approach for the else condition is essentially the same, so I'll copy and paste, except this is array B and we're using B pointer, and then we've already dealt with that element in array B, so B pointer gets incremented. Question so far?
So we've dealt with all of the cases up until we've exhausted one of the arrays. Say in array A we have the elements 2 and 4, and in array B we have the elements 5 and 6. So the resulting merged array should be 2, 4, 5, 6. In this while loop, we look at the first elements. Array B is less, array A is less. We pull that element off, A pointer gets incremented to 1. So now we're looking at element 1 in A pointer in array A, and element 0 in array B. 4 is still less than 5, so we grab that element. A pointer is 2, B pointer is still 0. And we have 2 elements in our destination array. But this loop ends because A pointer is no longer less than A dot length. A pointer is 2, A dot length is also 2. That condition fails. So what do we need to do in order to take those remaining elements in array B and stick them in destination? Right? So we actually have 2 cases here. One case is where we have elements remaining in array B, and the other case is where we have elements remaining in array A.
So, and there will never be any other case. We will always get to the end of one array first. So first we'll check if A pointer is less than A dot length. That means that there are still more elements in array A. And that means we want to copy from A at index a pointer to a dot length. Oh no, a dot length minus 1. That's how I'll denote a range. To destination. What's the first index? It's still a pointer plus b pointer. And we want to copy to destination, and it's basically des.length minus 1.
Right. And because of the way we've copied everything so far, those sizes should match up. There should be no issue there. We're going to cheat a little bit, and it turns out that there is a function in a method in Java, built into Java, that allows us to copy from one array to another. Just kind of, it happens. It works.
That is called system.array copy. It would be really, really cool if the book used that. It does? It does not. No, it does it essentially manually. So we'll use system.array copy. This is a method that takes 5 arguments.
The first argument is the source array. The second argument is the index, the starting index in the source array. The third argument is the destination array. The fourth argument is the starting index into the destination array. And the fifth argument is the number of elements to copy.
So where are these coming from? These are coming from A. Where are we starting? That would be a pointer. Where are they going? That would be dest. What index into dest are we starting at? That would be a pointer plus b pointer.
And the last argument is the tricky one. How many elements are we going to copy? So let's take the example that we had before. A is 2 and 4. B is 5 and 6. B pointer is 0. Let's switch the array so that we're using the same names. So 5 and 6 is an A. B has 2 and 4. We've exhausted B. A pointer is 0 because we haven't copied any elements from A to dest. The length of A is 2. We want to copy 2 elements. That sounds a lot like a.length minus a pointer,
Which is correct. It not equals. That won't work. A pointer.
It would be equivalent to, say, dest.length minus quantity of a pointer plus b pointer, but that's a lot of opportunity to mess up.
So a length minus a pointer. And it also helps us out in case we accidentally somehow made dest too long or something. In the other case, if b pointer is less than b.length, we do exactly the same thing with some slight differences. Right, instead of copying from A, we're copying from B at B pointer. We're still copying to destination. We're still copying to the index into destination that is the sum of the quantity A pointer plus B pointer. But in A length minus A pointer would be 0. That's not right. So it's B dot length minus B pointer. And let's clean up some of our code here so it's a little more readable. And this comment is absolutely useless. It doesn't say anything, any useful information.
And that is our merge method.
So,
show of hands. Who thinks this is going to work?
Ah, good point. Yeah, so if we compiled it, it would say, you can't do that. What are we going to return?
Dest, right?
That's where we're copying everything to. And that compiles.
Okay, so now, show of hands. Who thinks this is going to work? I see you all have the utmost confidence in me. Who thinks this is not going to work? Okay, that's not so terrible. Anyone want to take a side? No. Okay.
Yours doesn't work. Okay. I already did that. Right. Oh, geez. That's pretty cool. It's a lot more numbers than I put in. So now we can have fun debugging. And I imagine I can probably guess as to... I can make a guess as to where the error is. It's... Oh, that's... It's... We'll start there. We'll start with that kind of debugging. Hang on. What's going on? Okay. That looks a little better. Strum. Okay. That's better. Okay, so where's the issue? Oh, geez. I forgot to put a space there, didn't I? I need that to be a string. Let's just put the space there. Okay, so okay, so if we follow this tree down, we start with that half, which is right here, split that in 2 halves, and we get, that's the left half, 7 and 3 and 12, that makes sense. 4 and 1 is the other half, and that all gets merged back together. Then we have 9, 2, 5, 10, 6, which makes sense. Then we get what is going on here. And so, can anyone see what my error is? If I can find, yeah, here we go. That's my error.
That's bad. That's very bad.
What do I need to put there?
Certainly not 0.
That makes more sense, right? So now let's see if we get something a little more sane. And now this looks more sane as well. We break this in half, here's our first half, break that in half, here's our first half, break that in half, here's our first half, deal with that. The second half is right there, the second half of this line is right here, and then the second half of the whole thing starts here, divide that in half, we get 9, 2, 5, divide that in half, we get 9, 2, and 5, which we deal with, and then the second half of this is dealt with right here.
Questions? Are you sure? So if I had a question on the exam, which you already all know that there isn't, but if I had a question on the exam on how merge sort works, you would all be able to explain exactly how merge sort works.
Absolutely. You just spent an hour explaining it, so it's pretty easy.
I know, isn't it?
And the book only talks about it in, 5 pages or so. Alright. Yes.
I think that's sufficient for today's class.
You can take a break and you can come back if you want to.
Homework due today. If you have questions on it, feel free to ask me those questions. Otherwise, we've already mentioned that recursion really isn't on the exam. So there's no additional exercises today. You can work on programming assignment 7. You can study for the exam.
Or you can disappear.